Hello, my name is Nikolai Karpov, and I am going to present our joint work with Zhang and Yuan Zhou on collaborative top distribution identifications with limited interaction. So let's start. One of the main fundamental questions in the machine learning is to make machine learning algorithms scalable or distributed. One of the reasonable ways to introduce the scalability in our algorithm is the following. We can introduce a lot of agents in the learning process that will work simultaneously and optimize the objective function in collaboration. As we know from the real life, the collaboration between agents or people in real life can be extremely useful, but it also can be very expensive. In the context of machine learning algorithms, when I speak about the usefulness of collaboration, I mean that agents in collaboration can improve the quality of an algorithm. In other words, decrease the probability of the error of our algorithm or increase the convergence rate. When I speak about the expensiveness, I mean that in distributed algorithms we have a big overhead each time when agents try to communicate with each other. Because in distributed systems, we have an overhead related to network bandwidth, latency, or synchronization, and so on. And motivated by these two items, we're interested in a trade-off between the number of rounds of communication and the quality of our algorithms. So let me introduce the specific problem on which we focus in our work. In our work, we consider one of the most fundamental problems in the area of reinforcement learning. In our work, we consider the top M identification problem in multi-armed bandit settings. In this problem, we are given a set of n arms, where each arm is associated with an unknown distribution and has support on the segment 0, 1. We want to find the set of m arms that has the largest means. In the multi-armed bandit settings, we can only get information about distributions by pulling arms. And when we pull an arm, we get an ID sample from the associated distribution. In the multi-armed bandit settings, we assume that each pull takes a one-time step and ignore other kinds of computation in the running time. Specifically, we are interested in minimizing the probability of the error if the running time is fixed. In other words, when the total number of pulls is equal to t. Now let me speak a little bit about the collaborative model in the context of multi-armed bandit settings. In this model, we additionally have k agents, and the learning process is split into rounds. In each round, agents work independently and make pulls. After that, at the end of the round, agents communicate and start the next round. Note that in the iter round, each agent makes ti pulls. At the end of the algorithm, agents communicate and output the answer. For our specific problem, it is the set of m arms with the highest means. Let me recall. As I said before, we are working in the regime when the running time is fixed, and we try to minimize the number of rounds and the probability of the error. Clearly, there is a trade-off between these two values. So, if we increase the number of rounds, then the probability of the error should decrease, because agents can exchange more information and they have more freedom. Also, note that according to our model, in total, agents make t times k pulls, because the value t is the bound on the running time of one agent. Now, let me turn to a brief summary of previous results. In the standard model, that corresponds to the case when k is equal to 1 and we don't have any communication, the best result has the following form. The best known algorithm for the fixed running time t achieves the following probability of the error. Here, h is a value that is known under the name of the instance complexity in the reinforcement learning literature. If we look at the collaborative model, this model was studied in the recent paper by Zhang and Zhou for the best arm identification problem, and it is a special case of our top M problem where M is equal to 1. So, in their work, authors proved that there is an algorithm that for any R achieves the following error of the probability by using big O of R rounds. Now, I would like to compare our new result with the previous result of Tao et al. So, we provide the algorithm for the general case M. As you can see, the guarantees are pretty similar, and for small m, we achieve almost the same guarantees. Here, the parameter r controls the trade-off between the number of rounds and the probability of the error. However, when m is large, we have additional term log of log m over log k in the round complexity. And I would like to note that both of these results are almost tight and achieves the best trade-off. And to highlight the difference between our algorithm and the previous one, I will set the parameter r to the specific value. I will set it to be equal to 2. In this case, we can see that if we want to achieve such the probability of an error with the square root of k factor in the exponent, then in that case, we have that for solving top 1 problem, we need only a constant number of rounds. However, in the general case, we need at most log of log m over log k rounds. In our work, we proved that such a number of rounds is sufficient and necessary. We proved an upper and lower bound that are almost tight. Thus, we prove the strong complexity separation between the case when m is equal to 1 and the general case of the problem. It is pretty surprising, because in other models, such problems usually have similar complexities, and these problems don't have such gaps. Now, I would like to formulate our result in the general form. In our work, we proved two main results. Firstly, for any r from a reasonable range, we can construct the algorithm with the following guarantees. And secondly, we proved that the lower bound that says that this algorithm is optimal, and there is no algorithm that can significantly outperform one. Both of these results are highly non-trivial and require new ideas and techniques. However, because of time constraints, I will be able to highlight only some parts of the upper bound. Moreover, I will focus only on the specific case of our algorithm when r is equal to log k. In this case, the guarantees for our algorithm transform in the following way. The term R in the round complexity transforms to log k term, and the factor in the error probability from k to the power r minus 1 over r transforms to k. And before I will present some description of the algorithm, I would like to highlight the issue with the previous approach of Tao et al. For the top one problem, in the situation when we try to generalize this approach for the general M. In the previous algorithm for top one, the algorithm follows the next strategy. At first, it randomly splits the instance into k parts and tries to solve the top one problem on each subinstance. After that, the algorithm took the union of the answers and reduced the size of the instance. It's not the full algorithm, but it follows such kind of strategy. The analysis of this algorithm is based on the crucial fact that the algorithm can solve top one problem correctly on at least one subinstance, on the subinstance to which the best arm was assigned. In our case, the situation is absolutely different. If we split our instance randomly, then each subinstance will get a part of the solution. And we don't know for which m we should solve the top m problem on each subinstance. Moreover, we need to solve this problem on all subinstances simultaneously. Thus, the previous approach fails for our case, and we face big challenges in the case of the top m problem. So now I will describe a high-level approach to how we solve these issues. So our algorithm consists of three big parts. In the first part, we make reduction from the instance on n arms to the instance on c times m arms. Precisely, we extract a set of arms that contains the correct output and continue to work only with this part of the instance. After that, if the size of instance is large enough, we reduce the size of instance from t arms to the square root of t times k arms. And we do it until the instance becomes small enough. After that, we solve the remainder instance on poly of k arms by using a low-adaptive algorithm. I would like to highlight that the item 1 and 2 are the main challenges of our algorithm. This reduction requires a lot of new algorithmic ideas and pretty delicate analysis. And before I go into explanation of these details, I would like to say a couple of words about the round complexity of this algorithm. The item 1 and 3 in total requires big O of log k rounds, and each reduction in the loop for item 2 requires a constant number of rounds. However, we need to repeat this reduction approximately log of log m over log k times, and in total, this step requires log of log m over log k rounds. So now I would like to briefly describe what happens inside the reduction from item 2, how this reduction works. So let's start with some brief description on how it works. So firstly, the algorithm randomly splits the instance into k parts. After that, for each sub-instance, agents solve an approximate version of the top new problem. And in the end, agents combine solutions and, as a result, remove some arms from the instance. So it is a brief plan, and let's go into the details. As I said before, at the first step, we randomly split the instance into k parts. On the figure, I showed how arms from the big instance with mean status are assigned to the agent. And each agent gets approximately t over k arms. Thus, each agent gets some set of arms such that the arms above threshold on the picture should lie in the correct output, and arms below the threshold shouldn't belong to the output. After that, we pick two pivots elements, A and B, and for these elements, we identify the two sets of arms that lie in a small epsilon neighborhood of these pivots. We identify the right set of arms that have a large means and belong to the output, and add these arms to the output. And we identify the green set of arms that don't belong to the output. Finally, we remove all red and green arms from the instance and reduce the size of the subinstance. After that, we take the union of all remaining arms among agents and reduce the size of our instance to the targeted value, to the square root of t times k arms. As you can see, we have a freedom in the choice of the epsilon. And actually, epsilon is not a fixed value in the algorithm. It is a random variable that depends on partition and determines adaptively for each sub-instance. The analysis on epsilon and concentration results on values related to this epsilon is the main challenge of the analysis for this reduction. And additionally, the approach that I described gives us only a constant error algorithm. When t is large, we are targeted to the probability of an error that decays exponentially in t. And the barrier why we cannot apply standard techniques to amplify this constant probability is the following. We don't know the value of the instance complexity at the beginning of the algorithm. It is a new challenge for our algorithm. Now, I will briefly describe the framework on how we achieve the small probability of an error. So let's go to the framework. Firstly, we try to guess the value of the instance complexity of a k. And for each guess h, we run approximately t over h copies of the algorithm. If the budget is large enough, then the answer of these copies of the algorithm will be consistent. In other words, the correct output will be returned by at least half of copies. It gives us the following approach on how to choose the best answer. We just pick the consistent answer for the smallest budget where the algorithm outputs the consistent answer. However, there is an issue with such approach. If the gas H is small, then the wrong output can be consistent. And with the goal to remove this issue, we develop a new framework, Guess and Verify. On the next slide, I will briefly describe the idea of this framework. So let's go to the next slide. In this framework, we introduce a new notion of a certificate. And now each algorithm, together with the answer, will output the certificate for the answer. After that, independent algorithm that we call a verifier checks the certificate and catches wrong outputs. This approach secures us from the consistent wrong answer if the budget is low. And so on, we can amplify the probability of an error. So at this moment of time, I finished with the upper bound. And now I would like to say a couple of words about our lower bound. In our work, we prove the following lower bound. This lower bound complements our upper bound, and we can see the full picture for the top M problem. Our lower bound is a key result for understanding the complexity of the top M problem in the collaborative model. This result shows that identifying the position where the algorithm should split instance into two parts is the hard task, and the complexity of one depends on the value of M. Unfortunately, in this presentation, I don't have a chance to speak about details of the lower bound. However, I would like to highlight that this lower bound requires a new and nice ideas, with a fancy hierarchical construction of the hard instance. So, if you're interested in details, then I would like to encourage you to read our paper. Now, I finished with the discussion on our results, and I will move to the next slides to summarize the main contributions and messages of our paper. As I said in the presentation, for the fixed time regime, when we fix the running time t and minimize the probability of mistake, we achieve a tight upper and lower bounds for the top M identification problem. Also, we show the strong separation between the best arm identification problem and the top M arms identification problem. Additionally, in our work, we also consider the fixed confidence version of the problem, when we fix the probability of error and minimize the running time. In that regime, we develop an algorithm that matches with the lower bound. Also, we prove the separation between complexities in fixed confidence regime and fixed time regime. Also, I would like to highlight that the collaborative model is a new one. In our work, we show that even such generalization from top 1 to top M needs a lot of new ideas and techniques. There are a lot of problems in reinforcement learning for which we don't understand the situation with the speed up that collaborative learning can bring, and it would be nice to understand once. So actually, it is the end of my presentation. Thank you for the listening.